we present virtual elastic objects. Imagine you're in a room and put on VR glasses. In a seamless experience, you will be able to see the objects in this room in the virtual world too. While it is a hard problem to make this happen, we could do so by using techniques for 3D reconstruction. Most importantly, we could leverage the real-time information from sensors in the room to update the rendered object at all times, in particular while you're interacting with it. Imagine squeezing a pillow. It gets tricky, however, when you want to pass this object seamlessly to a friend in VR. If we 3D reconstructed the object, this might be just as easy as passing the 3D model on. However, the object will not be able to react to new interactions. The pillow now becomes as rigid as a rock. Even sensor data cannot help here. That's where virtual elastic objects come into play. Virtual objects not only looking like their real-world counterparts, but also behaving like them. We create these objects in multiple steps: capture, reconstruction, learning material parameters, generalization to novel interactions, and finally, rendering of the objects. To capture the behavior of the object, we actuate the transparent fishing line attached to the extremities of the object, such as pulling the fins of the fish backward and forward. Then we cover the object's surface with a compressed airstream while tracking stream origin and direction. With these recordings, we assemble the plush dataset. It consists of the recordings of 12 different objects, including a pillow, a sponge, and of course the name-giving plushies. In the second step, we do a 4D reconstruction of the objects using non-rigid neural radiance fields. We 3D reconstruct the objects in space and also recover their deformation fields over time. Here, we show the reconstructed point clouds of all objects in the dataset. Their geometry and color closely match their real-world counterparts. The next step is to learn the material parameters of the objects through a differentiable physics simulator. Again, we visualize the reconstructed material parameters for all objects in the dataset. The color represents the stiffness of the material, with darker purple tending to softer material and yellows tending to harder material. Our method identifies different material properties of the objects, for example, at the ears and on the arms of the baby Yoda, for the tail of the fish, and the mane and tail of the pony. Lastly, we simulate the reconstructed objects interacting with secondary objects in novel settings with a learned physics model and render these new deformations using non-rigid nerve. We show a comparison of the renders between the reconstructed point cloud and the simulated point cloud under an external force field for the pillow. The simulation result matches the reconstruction from the non-rigid radiance field closely. Now we show a collection of results of our virtual elastic objects interacting with other virtual items. Here you can see the deformation of the plush fish poked by a virtual stick. We loop the video back and forth to show the response more clearly. Here's another example with a dinosaur plush toy. Notice how the head of the dinosaur turns in the end, which is similar to what we expect for the actual plush dinosaur. This is our last example of interaction with secondary objects. An item is colliding with the top of the plush Shiba, and we can see how its surface deforms according to the shape of the item. Thanks for watching.